Hello, welcome back to the channel. So let's do one more interesting word problem based on differential equations. So you have been given that a certain continuous function, which is denoted by y is a function of x, it also satisfies this integral equation over here. So the key points in this y function consideration are, first of all, our function is continuous, and also it satisfies this integral equation over here for all x in some open interval containing 0. So this line gives us a hint that we'll probably be using x equals 0 at some point in order to solve for our solution. And based on this integral equation, you have to solve for y as a function of x and also calculate the largest interval for which this integral expression, this integral equation holds true. So now in this case, it's a tricky problem, right? Because we are not given the differential equation, and we first want a differential equation in order to solve for y as a function of x, right? And we know that we know how to take the derivatives of integrals, definite integrals. So we can take the derivative of this expression over here, this integral equation. If we take the derivative of this integral equation on both sides, we'll get dy by dx on the left hand side. So we have a component for our differential equation. And if we solve for the derivative of this expression, we can easily solve the derivative of this definite integral over here, because the derivative of 3 is 0, so you'll eventually have to solve for the derivative of this definite integral over here, which we already know how to solve. So before watching this video, I'll highly suggest you to first watch my previous videos about some word problems that we already did so far in the previous videos, and also how to take the derivative of definite integrals in an easier way. So now we know that in order to get the differential equation, we'll have to eventually take the derivatives on both sides and we'll get the differential equation. We'll see how it looks like, but we know an idea how to get the differential equation at the end. So now we have the differential equation. There is also one more important thing, which is known as the initial condition, right? And we know that in order to get the initial condition, we'll have to know at least one x and y value which will satisfy our y of x expression over here, right? So using this integral equation, we can use an important fact about integrals, about definite integrals specifically, that if you're calculating the integral of f of x dx from x equals a to x equals a again, it's always equal to 0, right? So now in this equation, if we substitute x equals 0 over here, we can get rid of this definite integral expression as well, right? So that is why if we substitute x equals 0 in this equation, this integral expression will be equal to 0. So you'll get y of 0 as simply 3 in this case, right? Because you can clearly see that if you have x equals 0, your y of 0 would be simply 3 plus integral 0 to 0 for this weird expression over here, right? So this would be this expression over here. And this integral from 0 to 0 is 0. So you'll get y of 0 as 3. So now you have your initial condition as well, which is this expression over here. So now let's take the derivative on both sides for this integral equation and get our differential equation. So let's write the integral equation again. Our integral equation is simply y of x equals 3 plus integral 0 to x y of t square minus 3yt plus 2 times sine t dt in this case. And we can take the derivative on both sides. So derivative of y of x will be simply dy by dx, right? And derivative of 3 is 0. Derivative of this integral, I'll solve it quickly because we already know how to solve for the derivative of definite integrals. So this expression will be simply y of x square minus 3 times y of x plus 2 times sine x in this case, right? And since we know that our y is equal to y of x, which is given over here, your y is a function of x, so we can simplify this equation and can write this equation as dy by dx equals y square minus 3y plus 2 times sine x in this case. And now you can solve for this quadratic equation over here. Because we want to solve for this separable differential equation, we'll have to eventually move this quadratic equation to this side and this dx over to this side. So if you do that, you'll get dy upon y minus 1, y minus 2 in the denominator, and sin x dx on the right hand side. And now since you are dividing the left hand side by this expression over here, you have to add a constraint that your y is never equal to 1 and it's also never equal to 2 as well, right? So that is an important point that we'll have to consider. And now once we have this separable form, we can take the integral on both sides and we can solve for our y as a function of x. And then you can also use the initial condition, which is y of 0 equals 3, to get the final y in terms of x. And if you'll solve that, you can solve this integral using partial fractions, and you know that the integral of sin x is minus cos x. So we'll not do this indefinite integral calculation completely, but the answer, when you'll solve this differential equation, you'll get this expression over here. Because when you'll apply partial fractions to this expression over here, you'll have a log form, right? And whenever you have a log form, you always have an absolute value inside the log function, right? So you'll get this expression over here, and there is an important consideration that you have to make in order to get rid of this absolute sign on the left hand side. You cannot straight away get rid of this absolute sign, because you know that when we are getting rid of these absolute value signs, we always add a plus minus term over here, right? So now in this case, you can clearly notice that the right hand side, since the right hand side is an exponential function, it can never take the value of 0, right? So that is why if our right hand side cannot take the value of 0, our left hand side would also never take the value of 0 as well, right? And we also know that when our x is equal to 0, this expression is 1 by 2, which is also positive. And we also know about one important fact about the y function over here, that it is a continuous function over here. So now using all these concepts that we already know about y, we know that since y is a continuous function and the left hand side cannot be equal to 0, so y cannot be equal to 2 in this case, right? And also if y is a continuous function, it must remain larger than 2, right? Because if your y is a continuous function, it has a continuous graph, and we also know that our y cannot be equal to 2. So that is why in order to have y values which are lesser than 2, since y is a continuous graph, if you want to get y values which are lesser than 2, you'll have to eventually pass through the y equals 2 point, right? But we know that y is a continuous function, it does not have a break point. So that is why if y can never be equal to 2, we cannot have y values which are lesser than 2 as well, right? I hope that makes sense. Feel free to comment down in this video if you have any doubts about this important consideration over here. So since we know that our y is always greater than 2, this expression is always positive. Because if your y is always greater than 2, you know that your numerator is always positive and your denominator is also always positive. So you can absolutely get rid of these absolute value signs on the left hand side. So you'll get eventually this expression over here, and if you'll solve for your y in this case, you'll get this final equation over here. So this is the answer to your first part over here. So now you have found y as a function of x. You can clearly see that in this expression you have y as a function of x. And since this is a longer problem, let's divide this video into two parts. So in this video we have identified a y function in terms of x. Let's solve for the largest interval in the next video. So stay tuned for that. Feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.